This is a demo of Adaptive Computing's HPC Cloud On-Demand Data Center or ODDC product using the extreme scale scientific software stack or E4S Pro image that's running on Microsoft Azure. Now, ODDC provides a web-based interface for all aspects of managing a cluster. Here we see several clusters deployed using AWS, Oracle Cloud, Google Cloud, and even Microsoft Azure. On this Microsoft Azure cluster, I can see how it has been configured, and ODDC provides a dashboard. It provides a credentials manager where I can upload the credentials, a stack manager for building the software stack, a cluster manager, file manager. I can even see the accounting and instance prices on Microsoft Azure, so I can see in which region how much it costs to spin up a cluster. Now, you do not need to launch the cluster using any shell scripts or your own tools installation. Everything is done through a web-based interface. And it's a scalable cloud systems management solution that easily allows you to spin up this Microsoft Azure cluster, and it can take care of all the HPC cloud infrastructure resources and gives you an ability to launch your jobs using a web-based interface. You can even launch a VNC session on the head node of the cluster that you have deployed. It uses E4S as the image, the extreme scale scientific software stack, which is built using the Spack package manager, and using a set of HPC and AI ML tools, you have an image that you can connect to very easily using the VNC-based console. You can use the clipboard to copy text from between your host and the remote image. And let's see how we can use various packages. Now, Spack is the package manager, and I have in this image over 100 different HPC tools. These are tools that you may have already used, such as HDF5, MVAPICH, OpenMPI, OpenFOAM, Tau, Trilinos, PETSc, NetCDF. And you can use Python-based tools within the same image. Here are some examples. Let's just look at the setup for the cluster. There is a simple program, an MPI program for the message passing interface library. I have a MPI.h header, MPI init, finalize, and I'm just printing the rank and the size of the computation. I can compile it using MPI-CC, and MPI is in my path. I have a ODDC script to get the name of the nodes from the hosts file. When the cluster is launched, we have here 2 hosts, and then it will put it in the hosts.txt. I can specify that run this program on 2 MPI ranks using 1 process per node, using this host file, which is the hosts.txt that I just created, and run this application. So I can say run oddc.sh, and it will run it on the 2 nodes. You can see the node names are different, and these are the backend nodes, which are different from the node that you are on, which is in this case, this node name. So let's look at some AI ML packages that are included as part of this ODDC-based solution using E4S. So first, I'll go to a TensorFlow directory, and here is run.sh, and a simple TensorFlow example to show that it's using Keras, and here's a training. And I can say run.sh, and it will launch TensorFlow, because TensorFlow, PyTorch, and other Python-based products are already in your path in Python. So this is a platform for AI development. Now, TensorFlow, as you know, is a framework that makes it easy for you to build and deploy machine learning models. Here is the PyTorch example, and here is the f4.py script. I'm just importing PyTorch, and you can see the program. And PyTorch is a fully featured framework for building deep learning models based on the Torch library. And it's used for many applications like computer vision, natural language processing. And let's look at JAX. And here is the JAX simple neural net with Torch example. Here you can see the code. And so there are a number of AI/ML packages that are pre-installed in this distribution that should make it easy for you to jumpstart your development. But what happens when you have a need to deploy a cluster, install packages that are relevant to your application? Well, this is an extensible solution based on Spack and Python tools, and you can extend the set of packages that are installed over here in this image and add your own packages. So you can have like a union of the packages that are pre-installed in the read-only file system, and you can install new tools in the home directory. So let's have a look at what other packages we have in this distribution. JAX, as you know, is a high-performance numerical computation library that's built on top of NumPy. And it's a very fast library. We have the Python. I can import the TensorFlow, as you saw before, and I'm running this on Microsoft Azure, and I'm using various packages like JAX and Horovod, which is built using MPI, and PyTorch, but a number of other tools are included as well. So commonly used tools like NumPy or SciPy or Matplotlib, they are all part of this distribution. Let's see, OpenCV is also installed. Now, what happens when you need a package that's not included over here? Say you want the latest version of ChatGPT's OpenAI package from the ChatGPT interface using the OpenAI package. So you could say pip install -- user OpenAI, and then you'll be able to install it. The same package will be available on all the compute nodes. So let's go and use this. Now, OpenAI website allows you to look at this API key, and you can ask questions and have a conversational AI interface. So for example, if I said, say, multiply two matrices using NumPy, it can generate the code like this. So if I create a directory here, say NumPy, and I wanted to learn more about this, and I create a file, then I can just copy this code here from the OpenAI ChatGPT and then paste it here. So I can then say Python foo.py, and the same thing applies to many of the packages that you see. You could just ask the question. Now I can go to my settings over here in ChatGPT interface on my account, and then I can download a key that will allow me to programmatically interface with OpenAI. So here is the key that I have downloaded in this directory. And here is a simple example of connecting with OpenAI. So here I use this key and write an article on adaptive computing's ODDC. Now I connect to this and I print the message that I receive back from ChatGPT. So I can say Python example.py after this OpenAI package has been installed, and then it will say, oh, this API is no longer supported in OpenAI. You may want to use this install. Okay, I can say pip install -- user OpenAI equals 0.28. And then it installs this. Let me try Python example.py again. And there it is. So I just installed a specific version of OpenAI package, and I just said Python example.py, and it says adaptive computing's ODDC is a cloud-based IT infrastructure solution that provides businesses with reliable, secure, and cost-effective access to technology resources. Now, what is interesting about ODDC is that you can have jobs that can migrate from your on-prem clusters to the cloud, to one or more cloud providers using the MVAPICH solution and the Torque scheduler and ODDC for connecting to the different cloud providers, including Microsoft Azure. So in this example, we are able to connect to this. We are able to install a new package, change the versions. Let's see how it works with Spack. You see Spack is installed here. And if I say Spack find, you'll see that there are all these examples of packages that are installed. So if I said, for example, show me the location of tau, I can say Spack location -i tau. And then it will point out that it's installed in the /Spack directory. Now, this is a read-only file system. And if I want to install a new package, which is not over here in this list of 123 packages, I can simply look for that package. So I have Spack here. I can say Spack find, say, Valgrind. Valgrind is not installed on this. I can say Spack install Valgrind. And then it will install this package in the home directory, not in the read-only file system. And then we'll be able to see the new package, which is installed in the compute nodes as well. So this way, you can extend the set of packages that are installed. And in this case, it's going through the list of dependencies, it's concretizing, it's figuring out what needs to be installed. And it finds that it already has many of these packages that Valgrind needs, like bzip2, like zlib, like gmake, like boost, and it's using them from the /Spack directory. So it's not installing all of those dependencies again. It's just using the Valgrind source code, and it's downloading it, it's building it, and it will install it. Now, this will install in your home directory, so the other nodes can see the package. And we'll just see that instead of 123 packages, when I say Spack find, it will show me maybe 124 packages installed, including Valgrind. So it's building it now on this node, and we should be able to see that. There are other tools that we will see, including tools like OpenFOAM, which is a computational fluid dynamics package, or tools like PETSc and Trilinos and SuperLU, which are all installed using Spack, and we'll be able to use them together. E4S provides a platform where we can have a set of HPC packages pre-installed using the Spack package manager. And you can see that this package is now installed in the /home directory, which is mounted on the other nodes and not in the /Spack directory. But I can say Spack find and find that it has now 124 packages with the addition of this Valgrind that I just installed. And I can say Spack load Valgrind, Spack location -i Valgrind. And I can say Valgrind -- help. Spack find -- loaded. And it shows me that this package is loaded. Spack unload Valgrind. And if you were to go to another another node, say, let's say etc hosts, and I can just SSH to any of these two nodes. So if I go to SSH here, on this Azure node, and I can say Spack load Valgrind, it's then visible over here. And this is on the compute node. And it may take a little time for the first time. And I can say Val. There it is. So both the host and the compute nodes have that package. Let's go and see some other tools. Here is OpenFOAM. And let me just run an example over here. And it's running block mesh example. In this case, it's generating the data, and then it's going to launch the GUI of ParaView. So ParaView is a visualizer which is launched by ParaView, which is launched by the foam view. And then I can look at open this eye, and I can then see, say, the surface with edges and the grid and the three-dimensional view of this. There are other examples that you can look at. Maybe I can look at the ParaView itself as a tool. And it comes with several example cases. Here's example visualizations. And everything is running on the cloud. That is the interesting part. We have other tools such as Visit that are also part of this distribution. Here is the Visit GUI. So I can open up, file, open, example.silo and add, say, a pseudo color for pressure and draw it. So here I can see the three-dimensional view with all the rendering that's taking place remotely. And here I can say create a slice with an ISO surface and draw it. And you can see that output. So let's look at some examples for using the numerical libraries. We said that there are a number of these libraries that are present. There is a simple PETSc example for solving a set of linear equations, Poisson equations in 2D. And to compile this program, I have a compile.sh file where I'm just saying, I'll say use make ex50. And then I can say clean.sh, compile.sh. And here it will look at the location of PETSc. It will use the MPI compiler, MPICC, and create the executable called ex50. Now, let me just launch this on the two nodes, again using the host.txt file that we had created. And it's saying use 4 MPI ranks, 2 processes per node, and use OpenMP threads as 2. Use this, and I can say run ODDC.sh, and it will launch this. Here, let me Spack go to a new session and launch the MPI. Is a terminal, and make sure that I have the MPICC installed over here. And I can go to the examples. Let's see, CPU, clean.sh, compile.sh, using this MPI. And I need to have this correct MPI run in my path. I may have had different MPI loaded. And now I'll just say run oddc.sh. And it will be running this on the 2 nodes that we have allocated using the Azure's backend nodes, and it's running this. Now, if I wanted to measure the performance of this, I can use run tau ODDC script that I have. And in this case, I am saying, please use the same application ex50, but launch it with tau exec with event-based sampling. Tau is the performance evaluation tool package that's integrated. I'm also setting tau call path as 1, tau call path depth as 100, so that I can see all the calling sequences of the functions. And I'm also using the perf stubs interface that comes with the PETSc library. With this, let me launch this run tau oddc.sh, where I'm using the 2 compute nodes on Azure, and then I will use an uninstrumented binary, which has been using fully optimized binary with no additional symbols that I can use, and just launch it with tau to measure the performance. I'll see the time spent in MPI, the time spent in the application functions, look at the IO performed by the code, and then finally I'll have profile files that I can view in the Paraprof profile browser. So with this, I can see that there are, here is the tau interface. And if I click on node 0, it shows me exactly where it's spending its time. And there's a MATLU factor function, which is called through main stage, PC setup, MATLU factor. There's time spent in write V, and you can see where this time is spent through MPI. I send in write vector call for write, and then it's going to the libc.so, and all the IO that happens in this. If I want to visualize this in the Fed statistics table, I can see the time spent here. Let me just expand this. And you can see that if I click on this inclusive time, is this MPI calls over here. And in main stage, you can see that it spent 27 seconds. Out of that, PC setup, KSP solve, which took about 5.4 seconds. In PC setup, it called MATLU factor, and you can see the distribution of this 11.5 seconds across the different functions. And MPI test, MPI send, MPI wait. You can even go inside the MPI wait. You can see all the IO and where it's spending its time. In all gather V, you can see the time spent in collective sync, which is the times wasted in a barrier call within a collective operation. So you can see exactly along which path, how much time was wasted in the barrier, say in units of microseconds. You can see that on node 0, thread 0, 84.3 milliseconds were spent here. Tau also has a 3D visualization tool, which is integrated in Paraprof, and here is an example of that. Instead of looking at the performance of the code, these two-dimensional charts, I can say, show me the 3D visualization, and here I can see the bar plot, I can see the scatter plot, topology views, triangle mesh, and it's showing that these two functions are kind of inversely correlated to each other, and there's one rank that is doing something different from all the other ranks that are shown here. We see the MPI ranks along one axis. There are 256 of these, the functions and the time spent in different functions along the z-axis. And you can see that function, which is taking a lot more time on one CPU. So 3D visualization tools, all the tools for AI, ML, and HPC are integrated. There are other applications that are also part of this distribution. Here is the LAMMPS code. And LAMMPS is a large-scale atomic molecular massively parallel simulator. It is a classical molecular dynamic simulator from Sandia. And here is the in.lj file. And this is the input file. I can say run ODDC.sh, where I'll load up the LAMMP using LAMMPS package using the Spack command. And then I'll say run it on, say, 32 cores, maybe run it on fewer, run ODDC.sh. Instead of 32, let me say run it on 16 with 8. And then I can launch this execution, and you can see the application ran. There is Spack find Quantum Espresso. And you can see this Quantum Espresso package. And here is the run ODDC.sh. And instead of 44, let me just also say 16 and say 8. Use the two hosts over here and say run ODDC.sh. And this will run the Quantum Espresso package on the cluster. And Quantum Espresso is another quantum chemistry package that is of wide interest to the HPC community. Now, what is interesting about these packages is that we want to install them in the most efficient manner. Quantum Espresso, for example, with this package, we can calculate the electronic structure of real materials and their physical properties by ab initio method in this Quantum Espresso package. But when we run these MPI applications, we want to make sure that they are using the interconnect between the nodes in the most efficient manner. And also, intra-node, we are able to use this in the most efficient way within the same node. And to do that, we use the XPMEM package, which, unlike SHMEM, that it allows other processes to access the existing data, and it allows for a more efficient intra-node communication because the send buffer can directly be copied to the receive buffer. And XPMEM is the package that is used for intra-node communication in the MPI. So with this, you can run these applications, you can simulate them, and you can see the performance of your applications within the same image. There are other tools that are installed here as well. Here is the Julia example. And you can see in the demo, I can go to a Mandelbrot. And here is the run.sh. I can run Mandelbrot like this. And we'll be able to launch other languages as well. So here is the output from the Mandelbrot.jl. Simple example. We saw Python. We can say Spack find Rust. Spack load Rust. Which Rust? And you can see that Rust is part of this E4S distribution, like several other tools. There are other packages that are installed as well, like Spack find PAPI, Spack load PAPI, and then you can see tools like PAPI Avail, and it will show you which low-level hardware performance counters are available on this CPU, like PAPI L1 DCM or a level 1 data cache miss counter is available, and it's not derived from other native events. And you can use a number of different performance evaluation tools, such as Tau with PAPI, and see the full spectrum of packages that are available in this. So with this, I can show you the interface for ODDC, and you can see the dashboard here. And you can say, connect to the compute nodes. You can say nodus cluster SSH -- admin E4S 2. And then this will ODDC, which nodus? Cluster, sorry, not cluster. Admin E4S 2, and then you can connect to the compute node as well as the host login node, and you can say, this is Ubuntu user. You can sudo bash, and it will install Spack in the directory there, and you can assume the root privileges. So with this, I would like to just say that ODDC provides a uniform interface for all the different cloud providers. And on Microsoft Azure, we just saw how we can use a VNC-based login to connect to the login node and the compute nodes and deploy AI, ML, and HPC tools, including OpenAI's ChatGPT, as well as TensorFlow, PyTorch, JAX, Pandas, Horovod, and other tools. We can assist you in creating custom solutions based on ODDC.